This is the 26th video in our series on Lie algebras, and I think we're getting pretty close to the end. We'll probably have a 27th video, but that might be it for now at least. And if we revisit Lie algebras later, it'll be in the context of perhaps infinite dimensional Lie algebras. Okay, so what are we doing today? Well, we've seen Dynkin diagrams for a certain classical Lie algebras in the past. And now we want to look at Dynkin diagrams that might exist that we haven't seen yet. And today we'll classify all such Dynkin diagrams, but we won't see them attached to Lie algebras until next time. Okay, so anyway, we need some definitions first. So let's suppose that we have a real inner product space E, and then we've got a subset of vectors A inside of E, and it's a finite subset. I'll call those vectors V1 to Vn. And this set is called admissible if three things are satisfied. First, it's linearly independent. So we have a linearly independent set of vectors. Then they're unit vectors. So if you take their inner product with themselves, you get 1. And then if you take the inner product of vi with vj, if I is not equal to j, you get something that is non-positive. And then finally, if I is not equal to j, if you take 4 times the square of the inner product of vi and vj, you get numbers that are either 0, 1, 2, or 3. So that makes an admissible set inside of an inner product space. And now, to this admissible set, we can associate a graph, and I'll call that graph gamma sub A. And well, the vertices are associated to all of the vectors inside of the admissible set, so V1 to Vn. And then how many edges do you have between vertices? Well, you have 4 times the square of the inner product of Vi and Vj number of edges between the vertex associated to Vi and the vertex associated to Vj. And here's a really important fact here, and that is if we have a set of simple roots, in other words, a base for a root system, we'll call those simple roots alpha 1 to alpha n. And then if you take a set A, which is a scaled version of these simple roots, and we scale it by taking alpha over the square root of the inner product of alpha with itself, then this ends up being an admissible set. And furthermore, gamma A is the undirected version of the Dynkin diagram associated to the original root system. And I think this is all pretty clear just by the definition of the Dynkin diagram and the roots and all that kind of stuff. Okay, so now let's get into our first result, which is the following lemma. So given a graph gamma A associated to an admissible set A, the number of pairs of vertices joined by at least one edge is at most, that should be at most, the number of elements in A minus 1. So let's observe that that kind of graph over there is impossible. And that's because, notice that all 4 vertices are connected by at least one edge, but that's going to be more than 4 minus 1. Okay, so anyway, let's get to the proof. So what we'll do is take A to be equal to the set V1 to Vn, just as we had set up over here. And then we're going to introduce a new vector inside of the inner product space. And that new vector will just be the sum of all of the admissible vectors. So V1 added all the way up to Vn. Now this is not an admissible vector, but this is in the inner product space which the admissible set lives. Okay, and now let's observe that V is not the 0 vector. And we know that V is not the 0 vector because our set over here is linearly independent. But since it's not the 0 vector, that means if we take the inner product of V with itself, we necessarily get something that's positive. But now let's observe that what is that inner product of V with itself going to be? Well, notice that it's going to be something like this. We'll have the sum over I and j of vi interproducted with vj. But now we can split this into two parts. We can split this into the part where I is equal to j and the part where I is not equal to j. So let's do that. So we'll have the sum as I goes from 1 to n of the inner product of vi with itself. And then we'll have the sum over all cases when I is not equal to j. But the inner product is symmetric necessarily by the definition of an inner product. So we might as well put that in order, and then we'll pick up a coefficient of 2. Because like the inner product of v1 with v2 is the same thing as the inner product of v2 with v1. So we might as well add those together. And that'll give us an expression like this. We have 2, and then the sum as I is less than j, and they both run between 0 and n. Well, not really, because one is less than the other, of the inner product of vi with vj. So we've got something like that. But now let's observe, we know what one of these is. This object right here is equal to n, and that's because it's just 1 plus 1 plus 1 n times. But now let's observe, we've got n plus 2 times all of this stuff is bigger than 0. So that allows us to build the following inequality. So we have n is bigger than negative 2 times this sum over I less than j of this inner product of vi with vj. But now let's observe from this setup over here, where this represents the number of edges between vi and vj, that's going to be equal to the sum over all I less than j of the square root of number of edges from vi to vj, or really connecting vi and vj. Now let's notice that this sum is pretty clearly bigger than or equal to the number of connected vertices. But if n is strictly bigger than the number of connected vertices, then that means that the number of connected vertices is less than or equal to n minus 1, which is exactly this number. Okay, so let's see something that follows from this lemma. Okay, so here's something that quickly follows from this lemma. So gamma A, that graph associated to the admissible set, cannot have a cyclic subgraph. So we'll prove this by way of contradiction. So by way of contradiction, suppose that gamma is a subgraph of gamma of A, and it's cyclic. So I'll just say it is a cyclic subgraph. Now, if you don't remember what a cyclic graph is, that's okay, because we're about to see what that is. So now, before we see what a cyclic graph is, let's take A prime to be a subset of A such that gamma and gamma of A prime have the same vertices. So we don't know that they're the same graph, but they have the same vertices. Well, how do we do that? Well, we just take the cyclic subgraph and then pull off all the vertices and put them into this A prime. Now, we might want to just like give a name for these things inside of A prime. Maybe we'll have W1 up to WK. But now let's observe that we have gamma is equal to this cycle, W1, W2, W3, all the way around here to WK. And then, well, let's see, gamma of A prime is going to have this same general shape, except there might be some more connected vertices. Now, from this setup in this picture, we can immediately see that the number of pairs of connected vertices in gamma A prime is bigger than or equal to the number of pairs of connected vertices in gamma, but we can easily count up the number of pairs of connected vertices in gamma, which is equal to k. But now let's notice that k is strictly bigger than the number of elements in A prime minus 1. Well, k is bigger than k minus 1. And then Furthermore, because A prime is a subset of an admissible set, we know that A prime is itself admissible, but that contradicts this kind of maximum number of joined vertices that we had from our earlier lemma. Which means, well, we can't have a cyclic subgraph within a graph associated to one of these admissible sets. Okay, so now let's move on. Okay, so for our next example, we'll show that every vertex in gamma A is connected to at most 3 edges. So the following pictures are possible. So this is kind of obviously possible. Each vertex in that picture is connected to 1 edge. Here, each vertex is connected to 2 edges. We have a double edge. Here, a triple edge. That's okay. Here's another one where that middle vertex is connected to 2 edges. That's allowed. Here, we've got this middle vertex attached to 3 edges. That's allowed. But things like this are not allowed over here, and there are many, many examples of those as well. Okay, so let's get to the proof. So let's take an element V inside of our admissible set, and let's say that V is a unit vector. Oh, I guess we know that V is a unit vector just by this fact over here. And then let's suppose we have the following connection picture of things with V. So I'll write V right there. And then, well, let's say that it's connected like this. We have maybe a V1 that it's connected to right here, a V2 that it's connected to right here, a V3 that it's connected to right here, and then coming around the circle, a Vm it's connected to right here. So it's connected to M edges. So there are no cycles in this graph. We know that from our previous result. So that implies that as long as I is not equal to j, and well, these are inside of the set from 1 to m, we know that vi and vj are not connected. Because, well, that would make a 3 cycle, right? So if V2 and V3 were connected, we have a 3 cycle connecting to V. But what does that tell us? Well, that tells us that if we take the inner product of Vi with Vj, we're going to get delta ij. We're going to get 1 if I is equal to j and 0 otherwise. Okay, so in other words, the set V1 up to Vm is orthonormal. Okay, nice. And now what I'll do from there is take V, V capital, so this is going to be a vector space, to be the span of V, V1 up to Vm. So we know V1 through Vm is orthonormal, so we're adding this vector on right here that kind of is building this into a bigger vector space. And then what we'll do is take a new vector, V0, inside of V. So it's going to be a linear combination of the basis vectors here, so that the resulting set, and that resulting set I'm talking about is V0, V1 up to Vm, is orthonormal. So we're like completing this basis for V into an orthonormal basis. So the last chunk of it is already orthonormal, so we just have to like fix the V part, if you will. And there's the Gram-Schmidt procedure if you want to think about how that's done like precisely. Okay, great. But now what do we know? Well, now we know that we can express V in terms of this orthonormal set pretty easily. And it goes like this. So we'll have V is in fact equal to the inner product of V0 with V in the V direction, plus the inner product of V1 with V in the V1 direction, all the way up the inner product of Vm with V in the Vm direction. That's essentially how an inner product works to express things in terms of a certain basis. Okay, great. But now what we'll do is observe that if we take the inner product of V with itself, we get 1. Because as we talked about before, V is a unit vector because it's inside of A. Also, taking the inner product of v with this big expansion over here will give us a nice expression. Notice that we'll have the inner product of v naught with v squared plus the inner product of v1 with v squared added all the way up to the inner product of vm with v squared. That's pretty clear because we are just, inner producting another v onto this. And I just realized that should have been a v naught there. Okay, nice. But now I'd like to observe that this portion of the sum right here is most definitely non-zero. How do we know that's non-zero? Well, if this thing here were 0, then that means that v would be a linear combination of v1 to vm, but it's pretty clearly not by our setup up here. So that means that, like I said, that inner product has to be non-zero. But that means if we kick it out, we end up with something smaller. So that means all of this is bigger than the inner product of v1 with v squared added all the way up to the inner product of vm with v squared. Okay, but now let's observe that we know what the inner product of v1 with v squared is. Well, I guess we don't know what it is, but we know the possible values it takes. So it takes the value 1/4, 2/4, or 3/4, just dividing by 4 here. We know that it can't take on the value of 0 because v is connected to all of those. So I guess like built into this picture is the fact that I haven't drawn double and triple edges if they do exist. Okay, so that means we can replace all of those with 1/4 and we'll end up with something that is less than or equal to. Because if we've got double or triple edges, we could have 2/4 or 3/4. So anyway, this is going to be bigger than or equal to 1/4 plus 1/4 plus 1/4, so on and so forth. But how many times? Well, m times, because we've pretty clearly got m terms in the sum. So let's see what we have here. We have m over 4 is strictly less than 1. Because we got 1 way over here, but that means that m is strictly less than 4, which means that m can only be equal to 1, 2, or 3. Notice that I guess it could be equal to 0, but in our picture right here, we are assuming that there is some sort of connection. So let's see, we've got there, m is 1, 2, or 3, but m also counts the number of edges that are connected to this vertex v. So that means, well, we've finished this result. Okay, so let's move on. Now here's an immediate corollary that comes from this result, and that says that if gamma of a is connected and gamma of a includes a triple edge, then gamma of a has the following form. So, well, it can really only be like that, because observe that if we were to try to put some more edges into this, like an edge coming off of this and connecting to another vertex, then that middle vertex would be connected to 4 edges, which would contradict what we have up here. Okay, so in other words, if we've got a triple edge, we can only have 2 vertices and that triple edge between it. Okay, now let's move on to probably one of the most important lemmas for our upcoming technique. All right, so now, like I said, a really important lemma, it's going to be called the shrinking lemma. So it starts like this. So let's suppose that gamma of a has a chain subgraph. By a chain, I just mean this line here. So it's v1, v2, vm, and they're all connected by a single vertex as I've drawn. Then what we want to do is define a new set, which we'll call a prime. And what it is, it's going to be a with v1 to vm removed, and then you essentially replace v1 to vm with their sum. So that's what we've got here. A set minus v1 to vm, and then union this thing that I'll call v, which is the sum of v1 to vm. Then the result says that a prime is admissible, and its associated graph, gamma of a prime, is essentially the same graph that we had before, gamma of a, but now what we've done is shrunk the chain, which is that chain v1 up to vm, down to a single point. That's why it's called the shrinking lemma. We shrunk that chain to a point. Okay, so now, well, let's get to the proof. But let's observe over here, we know that we've got to show these things right here. Okay, so this first one, that any admissible set is linearly independent, that's pretty clear. So I'll just say A prime is linearly independent. And that's just like completely inherited immediately from the fact that A is admissible and thus A is linearly independent. Okay, so now let's go to this next bit. So we need that if you take the inner product of anything with itself from A prime, you get 1, and then this result as well. But notice that the inner product of almost anything with itself from A prime is already equal to 1, just by the fact that we're constructing A prime out of A. All we have to check is that the inner product of V with itself equals 1, because that's the only like new vector, if you will. Okay, but now we can take this inner product essentially the same way that we took a very, very similarly defined inner product of V with itself before. So let's recall that this is going to be the sum as I goes from 1 to m of the inner product of Vi with itself, and then plus 2 times the sum over all I less than j of Vi with Vj. Again, we did this calculation before. But now let's observe that all of these are equal to 1 by the fact that A is admissible, and we have m of them. So this is m. And then, well, we have plus 2 times the sum as I goes from 1 to m minus 1 of the inner product of Vi with Vi plus 1. Because those are the only connections we have are the two adjacents. So like Vi with Vi minus 1 and Vi with Vi plus 1. But this thing that we did where we only looked at I less than j means that we don't have to worry about both of those. This counts everything. Okay, but next up, let's observe that since we've got a single edge between these two, we know that this number right here is exactly minus half. That's because if we were to square it, we would get a quarter just by this rule right here. So that means that, well, it's got to be minus a half. We know that's negative from this thing right here. Okay, so anyway, that means that we have m plus, let's see, minus a half times 2, so that's going to be minus 1 times, well, m minus 1. So it's really m minus 1, which is 1, which is exactly as needed. Okay, so next up, let's note that if we were to take W not equal to V inside of A prime, then if we were to take 4 times the inner product of W with V squared, we're going to get what? Well, it's going to be 4 times the sum as K goes from 1 to M of the inner product of W with Vk squared. That's just by the definition of, let's see, V. But now let's go up here to this picture and observe kind of what's going on. We're putting a new vertex here, W, and we're looking at all the connections between the VKs and W. But observe that only one of those can be non-zero. And, well, that's because if more than one of them were non-zero, we would have a cycle. Let's pretend up here we had our W and it was connected to V1 and Vm. Well, then we would have a cycle, which we earlier proved that we can't have. So that means all of this is going to collapse to 4 times the inner product of W with VL, where VL is that one that's connected to W. Or if none of them are connected to W, then VL is just any of them. Okay, but anyway, now we know that since W is inside of, well, it's got to be inside of A, and VL is also inside of A, just by the construction of A prime, then that means that this is inside of 0, 1, 2, 3 as needed, and we needed a square there. Okay, so let's see, between all of the things that we needed to show and all of the things that are kind of obviously inherited from A, this is enough to show that A prime is admissible. Okay, so, well, let's keep going. All right, so now we're going to show that gamma of A cannot have more than one double edge, cannot have more than one branch, and it can also not have a combination of a double edge and a branch. And well, what do I mean by a branch? Well, I think it's kind of well named. It would be something that looks like this. So I would consider that a branch vertex. Okay, so let's prove this impossibility of more than one double edge first, and we'll do this by way of contradiction. So by way of contradiction, suppose that gamma of A has more than one double edge. Okay, but well, what does that mean? That means it has a subgraph of the following form. So we'll put one of the double edges at the extreme left-hand side, then we'll put the other double edge at the extreme right-hand side. But now let's observe that it has like a sub-chain inside of it. And so by the shrinking lemma, that means that we have some admissible, what I'll call maybe A prime now, although it's not exactly the same A prime as we had before because this is a subgraph of our original gamma of A, but it is an admissible A prime with the following picture because we just shrunk this big chain to one thing. But now let's observe that that's a contradiction. And that's a contradiction because that middle vertex is connected to four edges. So, well, that means that, well, we cannot have more than one double edge. Now, the rest of these are essentially the same. Let's maybe do this peach colored one first, more than one branch. And I'll just draw a picture. So let's say we've got at least two branch vertices. But if we've got at least two branch vertices, then that means we have a subgraph of the following form. But then, well, what can we do? Well, we can shrink this middle piece just like we had shrunk in the first setup up here to get the following picture. So we've got that kind of picture right here, and that's associated to an admissible set that we've constructed. But again, that's a contradiction, and that's a contradiction because, well, that middle vertex is connected to four edges again. Okay, cool. And then the case when we've got a double edge and a branch, well, again, that's pretty much exactly the same. In this case, I'll just draw the shrunk graph at the end, and it's going to look something like this. But again, that middle vertex is connected to four edges, which we earlier showed was impossible. Okay, let's keep going. Okay, so next up we've got a lemma which doesn't seem super connected to... Okay, so for our next lemma, we'll show that if we've got a graph which is a chain, vertices v1 to vn, and then we define this vector v to be v1 plus 2v2 plus 3v3 up to nvn, then if we take the inner product of v with itself, we get n times n plus 1 over 2. Okay, so let's see how this proof goes. So this is just purely a calculation. The inner product of v with itself. So we can do the same kind of thing that we did before. So let's split this up as the sum as k goes from 1 to n of k squared times the inner product of vk with vk. Observe that we've got this coefficient of k squared in this case, just based off of our definition of v, which slightly differs from what we had before. And then we'll have plus 2 times the sum as k goes from 1 to n minus 1 of k times k plus 1, and then the inner product of vk with vk plus 1. And again, we're doing the same kind of thing that we did before, keeping in mind that only v1 and 2 are connected, v2 is connected to v1 and v3, and so on and so forth, the same way that we simplified the sum before. Okay, great. So now let's observe that because we've got a single edge between all of the vertices, we know what this number is, and this number is minus 1/2. And then we know that all of these have an inner product of 1. So let's observe that in the end, that's going to give us the sum as k goes from 1 to n of k squared, and then minus the sum as, let's see, it's going to be k going from 1 to n minus 1 of k times k plus 1. Now, let's observe that we can't really push these together immediately because they don't have the same starting and ending point, but we can fix that real quick. Notice if we were to re-index this by replacing k with k minus 1, now it would be the sum as k goes from 0 up to n of k times k minus 1. But notice we might as well start that at 1, because if we started at 0, that's just a term that's equal to 0. But now we can push these two sums together and observe that it simplifies to the sum as k goes from 1 to n of k when all is said and done. But that's a well-known formula of k, or of n times n plus 1 over 2. All right, great. Now let's see what this lemma will help us do. Okay, so now we want to classify all possible gamma of A that have double edges. And what we'll see, it's pretty restrictive. So if gamma A has a double edge, then that double edge is at the end of the graph. So in other words, we've got a bunch of single edges and then a double edge at the end. Or it can be in the middle of the graph in only one case. And that is if we've got 4 vertices, a single edge, a double edge, and then a single edge. Those are the only ways that we can have a double edge. But now let's observe that that's corresponding to only 3 different types of Dynkin diagrams. So you could have this double edge at the end with the arrow pointing that way or the arrow pointing back this way. But then since we've got symmetry built into this, we might as well only consider the arrow pointing to the right for the other case. Now let's observe that one of these is type Bn and one of these is type Cn, and then later we'll call this Dynkin diagram type F4. And that's gonna be, well, associated to a root system of type F4 actually. Okay. So now how are we going to do this? So let's suppose gamma of A has a double edge. So if it's got a double edge, then that tells us, well, it only has one double edge and it can't have any branch vertices like we saw before, and it has to have the following form. So we'll call this vertex V1, this vertex V2, and then we'll go all the way up and we'll call this vertex Vm minus 1, and then this last vertex Vm, well, the last of the V's at least. And that's going to be connected via a double edge to vertex Wn, which is connected to Wn minus 1, all the way down W2 and W1. So we've put that double edge in the middle. Okay. So next up, without loss of generality, let's assume that, well, m is bigger than or equal to n, which, you know, we can make that assumption. Then let's set v equal to, well, the same kind of thing that we had it equal to before. So that's going to be the sum as k goes from 1 to m of k times vk, and then we'll set w equal to something similar. So that'll be the sum as k goes from 1 to n of k times wk. Those weighted sums of the vertices. But now let's observe immediately by our previous result, we have the inner product of v with v is m times m plus 1 divided by 2. Then the inner product of w with w is n times n plus 1 over 2. Okay, great. And now, well, let's look at this. The inner product of v with w is pretty easy to calculate. And, well, that's because the only overlap here is between Vm and Vn. So this is in fact equal to mVm and then nVn. Oh, and I guess I should say this needs to be squared here for our calculation. So I'll square it. But now let's observe that we can take the m squared and the n squared out, leaving us with the inner product of Vm with Wn. But then we know that there are two edges between Vm and Wn, and by this rule right here, we know that that means that the inner product of Vm with Wn squared has got to be equal to a half. So that's going to give us here m squared times n squared over 2. Okay, cool. So that's the inner product of V with W squared. Okay, so then also we can use something called the Cauchy-Schwarz inequality to make the following calculation. So let's start way over here on the left with m times n over 2. But let's see, that's going to be equal to 1 over mn times m squared times n squared over 2. I guess we're saying that both m and n are bigger than 0 in this case. Notice if one of them were equal to 0, then we would have this graph already. So we're really just proving that if neither are equal to 0, we get the graph right here. Okay, so anyway, now we can replace m squared times n squared over 2 with the inner product of v with w squared. So this is 1 over 2 times 1 over m times n times the inner product of v with w squared. But now we'll apply Cauchy-Schwarz to say that this is less than the inner product of v with v times the inner product of w with w over, we're bringing that m in along for the ride. But then look at this. We know the inner product of v with v and w with w, so we can use that. And that's going to give us m plus 1 times n plus 1 all over 4. Okay, nice. So now let's look at this. We've got this thing on the extreme left-hand side. M times n over 2 is less than m plus 1 times n plus 1 over 4. So now what we have to do is take this inequality and prove that that makes some restrictions on m and n. So let's do that. All right, so this is where we ended off. If we've got a graph of this form, then we've got this nice inequality involving m and n. Now let's multiply this out to see what we get. So we're going to immediately get 2 times m times n is less than m times n plus m plus n plus 1. Again, that's just from multiplying out both sides and clearing the denominators. Now I'm going to subtract a bunch of stuff from one hand of the equation to the other side. So let's subtract mn, m, and n from the right to the left. That's going to leave us with mn minus m minus n is less than 1. But I'm going to now add 1 to both sides to get mn minus m minus n plus 1 is less than 2. But now we can factor out this left-hand side, and we'll have m minus 1 times n minus 1 is less than or equal to 1. We're replacing that less than 2 with less than or equal to 1. But now from here, we'll see that we either have... But now from here, since m is bigger than or equal to n, we see that we either have n is equal to 1 or m equals n equals 2. Now, if n is equal to 1, then we have this first case up here. If m and n are both 2, then we have this second case right here. Thus, these are the only two possibilities. So now we've really restricted the types that we can have with double edges, or types of graphs we can have with double edges. Now let's restrict the types of graphs we can have with branched vertices. Okay, so now looking at graphs with branched vertices. If gamma A has a branch vertex, then it's one of the following types. So it's this Dn type that we've seen before, or this guy right here, which is E6, well, we'll call it E6. So it's this chain of 5 and then a branch happening in the middle. We have this chain of 6 with a branch happening, well, not quite in the middle, but 2 vertices in from the left. Same kind of thing down here, a chain of 7 and then a branch 2 vertices in from the left, and those are called E7 and E8. So let's start assuming that gamma of A has the following form. So it's going to start with a vector v1, and that's going to build up to a last v vector, which is VL. VL is going to be connected to this vector. VL is going to be connected to this vertex in the middle, which we'll call Z. I'll shade this yellow so that we see it's kind of a special vertex. And then building off of this, there'll be 2 different types of vertices. So over here, let's say we've got XM building all the way down to X1. And then building down this way, we'll start with WN, building all the way down to W1. And then, well, let's make some sort of assumption on the order here, which is without losing generality. And that is L is bigger than or equal to M, which is bigger than or equal to N. Now that we've done that, let's observe that what we want to show here is the following. So we'll either have M equals N equals 1, which points us to having a Dynkin diagram or a graph of DL in this case, or we'll have M equal to 2, N equal to 1, and L less than or equal to 4. And depending on the value of L, that's going to correspond to E6, E7, or E8. Okay, so now that we've got our general shape of our graph, let's define some weighted vectors just as we did before. So let's define x to be the sum of all k times xk, v to be the sum of all k times vk, and then w to be the sum of all k times wk, where k is ranging over the appropriate values depending on how many vertices of that type we have. And now let's notice something that's a bit different than what we had in the last case, and that is if we take the inner product of v with w, or x with w, or v with x, we'll get 0. And that's because none of those are connected because we've got this middle vertex which has a different name. Okay, so now let's define what I'll call v hat, which is going to be v over the magnitude of v, and then w hat will be similarly defined. So w over the magnitude of w, and then x hat is going to be x over the magnitude of x. So that means that v, w, and x form an orthonormal set. So let's get that written down. So like I said, v naught, w naught, x naught is an orthonormal set. But then what we can do is extend that to include, you know, the vector z in the middle, but it won't exactly be the vector z in the middle. It'll be like a linear combination of z with these guys right here. So we'll do this extension so that we have x hat, v hat, w hat, and then z naught, which is orthonormal, and it spans the vector space spanned by x, v, w, and z. Okay, so next up we can do something pretty similar to what we did before, which is write z in this basis. So observe that z will be equal to the inner product of z with v naught in the v hat direction, plus the inner product of z with w hat in the w hat direction, plus the inner product of z with x hat in the x hat direction, and then finally the inner product of z with z naught in the z naught direction. But now let's observe that this z inner producted with z naught cannot be equal to 0, because otherwise z would be in the space spanned by x, v, and w, which we know it's not just by our picture up here. Okay, but now we can do our calculation. Notice that 1 is equal to the inner product of z with z, which is pretty clearly going to be the inner product of z with v naught squared plus the inner product of z with w hat squared, I should be saying, and then the inner product of z with x hat squared plus the inner product of z with z naught squared. But then, like I said before, the inner product of z with z naught is not 0, so if we square it, it's bigger than 0. So that means if we drop it, we pick up an inequality. So we've got 1 is bigger than the square of all of those inner products. And now let's see what we can get out of that. Okay, so we ended with the following inequality. So this inner product of z with v hat squared plus the inner product of z with w hat squared plus the inner product of z with x hat squared was less than 1. Now, from here, what we can do is reintroduce the definition of these hatted vectors into the situation. So that'll tell us that the inner product of z with v squared over the inner product of v with v plus the inner product of z with w squared over the inner product of w with w plus the inner product of z with x squared over the inner product of x with x is less than 1. But now we can calculate all of these parts just based on a previous lemma, as well as, well, the way that z is connected to the chain from v to vl, x to xm, and w to wn. And it goes something like this. So let's see, this numerator right here is going to be 2 times L squared, and then we know that the denominator will be 4 times L plus 1. And that's because we know the inner product of V with itself is L times L plus 1 over 2, so that's where this 2 comes from. And then the inner product of Z with V squared is going to be L squared over 4, just based off this rule right here, how many edges we have here, and then the weighting of V. Okay, and then we get similar things here. So this is going to be plus 2 times m squared over 4 times m plus 1, and then plus 2 times n squared over 4 times n plus 1. So all of that's going to be less than 1. And then from here, there's a ton of symbolic arithmetic, and maybe I'll leave that as a bit of a homework exercise, but a ton of symbolic arithmetic will lead us to the following inequality. And that is L times m times n is less than L plus m plus n plus 2. But then another little spout of symbolic manipulation, which again I'll leave as a homework exercise, will bring us to the following inequality, and that is 1 over L plus 1 plus 1 over m plus 1 plus 1 over n plus 1 is less than 1, is bigger than 1. And this is the inequality that's going to take us to the end. So let's see how that goes. Okay, so this is the inequality that we ended up with. But now let's observe over here that we made this assumption that L was bigger than or equal to m, which is bigger than or equal to n. But now making a replacement here, we'll see that 3 over n plus 1 is bigger than 1. But now let's immediately see that that means that n plus 1 is less than 3, which means that n plus 1 is less than or equal to 2, which means that n is less than or equal to 1. But that means that n must be equal to 1. But notice both of those cases up there involved n being equal to 1. But from here what we do is loop this value of n back into this inequality. So observe looping that in, that's going to turn this object into a half. Subtracting it over, we have 1 over L plus 1 plus 1 over m plus 1 has got to be bigger than 1/2. But now we again have this ordering. So if we replace m or L with m, we'll get 2 over m plus 1 has to be bigger than 1/2. But now what does that tell us? That tells us that m plus 1 has to be strictly less than 4, meaning that m is less than or equal to 2. Well, really m is strictly less than 3, meaning m is less than or equal to 2. Okay, so that means our possibilities so far are the following. We have m equals 1 equals n, or we have this case when m equals 2 and n equals 1. Well, notice if m equals 1 equals n, then, well, we're just left with 1 over L plus 1 is bigger than 0. But of course, that's always true. So that means here that L is kind of free to be anything. Which means all we're left with is the case when m is 2 and n is 1. But now looping that back into our original inequality here, you'll see that we pretty quickly get down to the following point where we have 1 over 6 is less than L plus 1. But then you'll see that that means that L is less than or equal to 4, completing kind of our box that we wanted to show up there. So here's a big summary of what we saw today. So if you have a root system, then you can find a set of simple roots, in other words, a base for that root system. That base can be used to construct an admissible subset of the underlying inner product space. And then we saw that the graph associated to that inner product space, or associated to that admissible set, only had, well, all of those possibilities that we saw in the video today. But then that means that you can reverse engineer the possible Dynkin diagrams associated to the original root systems. And they come from the following list. So just as a summary, if R is an irreducible root system, then its Dynkin diagram is one of the following. So you've got A type, so an AN Dynkin diagram. We've got, well, this chain that we saw before. B type, C type, D type. And so we had seen all of those before. A, B, C, D were all associated to the classical Lie algebras. And then you've got these exceptional types as well, which we hadn't seen these Dynkin diagrams until today. So E6, E7, and E8. You've got F4 and you have G2. So I'd like to point out that E8 is super important in mathematical physics. Actually, lots of Lie algebra study is really important in mathematical physics, but E8 plays a pretty important role. Okay, so like I said before, we're almost done with this course. Most of what we have to do now is find Lie algebras associated to these exceptional type Dynkin diagrams, and then prove that if you've got a simple complex Lie algebra, then it is, well, one of the ones that we've seen before or one of these exceptional types, and then we'll be all set. And that's a good place to stop.